Hi, my name's Neel.
My name's Alisen.
Over here we have our RC low pass filter, which filters out high frequencies and lets low frequencies pass. Over here we were supposed to have a 1.5 kilo ohm resistor, but those were not included in our lab kit, so instead we used a 2.2 kilo ohm resistor and a 4.7 kilo ohm resistor in parallel to form an equivalent resistance of 1.5 kilo ohms. Our capacitance in our capacitor is 0.001 microfarads. As you can see here, we are putting in a very high frequency signal of 1 megahertz. As a result, most of it is being filtered out because this is a low pass filter. Now, if we do a network sweep, you can see the response starts to dip as we go further because, as you can see, if we increase the frequency, more and more of it is going to be filtered out.
This is our RLC circuit. This is the resistor of value 8.2 kilo ohms. This is the inductor of value 3.3 millihenries, and this is the capacitor of value 0.01 microfarads. The bandpass filter filters out all other frequencies except for a specific frequency. This is our waveform. Here we're inputting a 1 megahertz signal, and we get the original signal and the filtered out signal, which is the blue line. When we perform a network sweep, we can see that here the circuit prefers a specific frequency at 93 kilohertz and filters out the rest of the frequencies.
As you can see from this graph, the phase shift between the input and the response increases the further we go when we increase the frequency. This is because it takes a certain amount of time to charge up the plates of the capacitor. Therefore, if we have higher and higher frequency signals going through, the difference in time between the input and response increases.
The phase angle of the output signal leads that of the input by up to 90, right here, to the center resonance frequency, which is 0 here. It's in phase, and then it will change and lag the input to negative 90 here as the output frequency increases.